God. Hmm. So, greetings of the day to those who have joined, Dharmender ji, Ritik Pratap. So, last, first of all, so greetings of the day. I welcome you all to yet another doubt clearing or problem solving session. It's preponed to Friday. I had to leave on Saturday next day. So, today we are going to continue where we left off. So, we started discussing about smart grid protection and we were discussing about what kind of protection is really needed in this your uh, new smarter grids because of the proliferation or the deployment of DERs in the distribution side. So there is a backward flow which wasn't there previously. There was only power flowing from the transmission side to the distribution side. Now distribution is also feeding power. There is no microgrid who can work in islanded or grid connected mode of operation. So all of these things have created trouble in a sense that the relay engineers are unable uh, to correctly provide protection devices for these new smarter grids. So today we'll continue and we'll see what kind of uh, how can we improve the already present protection devices, and then we'll continue where we left off. Let me share my screen. It's visible, right? So yes, just a second. Two. Yes, now there's only one, and then it equates with. Probably that. Okay, so let's discuss why do we really need protection, and what is protection going to achieve for these new smarter grids with rapid deployment of DRs. So so assume that you had this distribution side where it's connected to a main grid characterized by this, which is at some voltage and frequency, and then you have loads, and then again you could feed power because there is a DR present. So now what's happening is uh, your whole protection scheme needs to be correctly manipulated because each bus there is a relay present. Let's say this is R1 and R2, and these relays should be able to adaptively protect your system in case there is any fault or any disturbance that occurs. Let's say in the last two buses connecting these two just a second. Is it happening? Yeah. Okay, so now what's happening is due to these DERs, now the current profile is changing. So the current profile is not same anymore. It could flow backwards, that is from distribution side, that is it can flow upstream instead of downstream, and sometimes the fault current that is being sensed by these relays is also changing. So that's what we discussed last time, right? So if this fault current is changing, which is being sensed by the relay, how will we be able to, how will the relay sense this change? Because this relay needs to operate in such a way that when the fault current exceeds a certain amount of this fault current exceeds a certain amount of threshold, it should be able to, for a particular amount of time, it should be able to cut down that line, cut down that system, so that the whole other part of the system remains intact, remains healthy. So if this current profile is changing, what we need is these relays. So these relays should become now adaptive. So what do I mean by becoming adaptive? It's that they should be able to sense how the fault current will change. If the fault current will change, then what could be the newer threshold? So they should be able to derive this threshold. So each relay in itself has two things. One is called plug setting multiplier and the other is time setting multiplier. The plug setting multiplier is basically your fault current upon pickup current. This multiplier tells you that if this PSM, whatever it's set on, it would tell us how much the current should exceed the fault current to be able to cut down, so that the relay would initiate a trip sequence, and the TSM adjusts the speed of the tripping. So now we are able to achieve two things. We are able to achieve how quickly or how slowly the relay would be able to trip, and second is how the plug setting multiplier will tell us what would be able to adapt to the fault current, which is changing with respect to how the DERs are uh, coming into being, right? So, yeah, so we now have achieved these two things, but still, what is missing? One thing is missing, right? So we can sense fault current, we can change it using the plug setting multiplier, we can change how quickly or slowly we want to trip the fault. What is one thing that is still left unchecked? Anyone? So the one thing that is still not checked is direction. So, so if these two relays, let's say, Devendra Okay, so that's great. I can mute people in Google Meet. That's good. So, yeah, where was I? So what I was saying is, let's say a fault is there on this in front of relay one, right? So this fault should be able to this the relay one R1 should be able to trip this fault because it's closer to it. So the relay one is what? Your primary relay, and R2 is your backup relay. So if we have two relays present in a feeder, we can use them as primary and backup relay for a fault belonging to that section or the other section, right? Now, based on this, we we may be able to sense the direction as well, right? So how the current is flowing, how the current is changing, and how this relays are sensing this current is something that can be used and to benefit us from uh, sensing a direction too. So we'll discuss on direction. One thing I wanted to discuss was how these two relays will communicate with each other. So there are certain standards as well. So there are certain standards as well. So these two relays should have a coordination time interval of how much, if anyone has gone through the PPT, can anyone tell? So coordination time interval is what? It's zero point 0.3 to zero point 0.5 seconds. And let's say that R1 is not able to cut down the fault, right? It's not able to sense that fault. Then R2 within this time frame should be able to coordinate with R1 and should cut down, should trip so that the fault is not there anymore. So the coordination time sets how much long can we withstand a fault if the primary relay is not able to sense that fault anymore. Right, so this is how these two things are. So these two are usually communicating with each other. It's relevant because if a fault is not being cleared, we need a backup supply as well. But now, if you look at it this way, let's say if R2 is not able to clear fault, you'll say that we can have a secondary backup as well, right? Let's have a primary, then a primary backup, then a secondary backup. That's not how some things work. So this coordination time interval, this backup relay will surely shut down, because once it trips, it will, what you say, it will be able to cut down the fault, because of the fact that uh, the whole feeder, even the healthy one, is not disconnected. So there's no chance the power will flow back, the power will flow through the fault. So the primary and the secondary relays, these two relays must be there in every system, providing backup to each other, coordinating with each other. But there are cases of miscoordination as well. There can be ways in which R2 will trip and R1 won't trip for a fault belonging to R1. So there are these research happening in this direction as well, because it's a booming topic, the adaptive protection, and people are still researching on it, that how can coordination between relays be improved, so that the distribution networks could have a better adaptive protection available to them. Right, but that's out of scope of today's class. We'll continue. So we discussed two things, right? We were able to change how we sense the fault current. We were able to trip the fault quickly or slowly. But now the problem arises: how do we sense the direction? We haven't yet figured this out, right? So to sense the direction, we the researchers at IIT Roorkee, so because this course is being taken by Professor Premlata, Jena, and NP Padhy, belonging from IIT Roorkee, they came up with this sequence currents based adaptive protection scheme, which is applicable to unbalanced fault only. So I'll tell you more about it, why it's unbalanced faults only. But because distribution systems are mostly unbalanced, this is a perfectly good assumption, right? So, so what they do is they try to figure out. So, uh, they try to figure out what is the operating time for primary relay and backup relay for a fault belonging to a particular bus and for a particular mode of operation of the microgrid. So this is a microgrid, this whole thing, and for this they are trying to figure out for each relay what can be a particular amount of operating time, and this operating time is usually less than 1 second. Yeah. So what is so this is a perfectly known, or you can say this is a known quantity. This is a known formula for deriving uh, this operating time of a primary and a backup relay. So this is a known formula. They have just taken this formula, but they made one change. What change they made was, for primary relay. This is for primary relay operating time, and this is for backup relay operating time. So what change they made was how the plug setting multiplier was interpreted. So for primary relay, they chose positive sequence current component for deriving the plug setting multiplier, and for the backup relay, they choose negative sequence current setting plug setting multiplier. So this is something that they came up with for unbalanced faults only, and um, yeah, so they used this phenomena and found better results. That's why they proposed that for backup relay you choose negative sequence component. Now coming back to my first question, so why do you think this scheme, this protection scheme, is only applicable to unbalanced faults? Why did I say that this is only applicable to unbalanced faults? This is the first thing that I said, right? Why is this only applicable to unbalanced faults? Anyone? With three people, right? So let's make this class lively. If you don't know the answer, let me know. Yeah. Okay.
Sir,
Tell me
please
one
repeat
thing.
the question.
Yeah, yeah, yeah. Yeah, go ahead. Okay. So tell me one thing. For this uh, sequence components are generally derived for which quantities? Can we derive sequence components for balanced quantities? Will there be a negative sequence component or a zero sequence component for unbalanced quantity? No, right? Uh, so,
Sir,
so
are
you
you
can.
asking question or telling?
I am asking question. I asked a question that I told in the beginning that this scheme is applicable only to unbalanced faults. And then
Yes.
then I told you that operating time for primary relay is calculated using positive sequence current component, and for the backup relay, the operating time is calculated using negative sequence current component. So, can you link both of these facts to come up with why scheme is only applicable to unbalanced fault? Because the negative sequence component will only be present if there are unbalanced quantities in the system. So when an unbalanced fault occurs, what is an unbalanced fault? If there is a single phase to ground fault, A to G fault, B to G fault. So if there is this, or let's say ABG fault, two phase faults, right? There can be. So if there is an unbalanced fault happening within the system, this quantity, the negative sequence quantity will be there. But if there is a three-phase to ground fault being happening, this is a balanced three-phase fault, right? So for a balanced three-phase fault, negative sequence current component will not be there anymore. So there you won't be able to calculate operating time for the backup relay. So I was just telling you how this scheme is applicable only to unbalanced faults. And their assumption that the scheme being applicable to unbalanced fault is perfectly valid because distribution systems are unbalanced in nature. But still, there are DRs connected to three-phase wires, and if these DRs experience faults, this type of protection scheme won't be applicable to them. So this was something that I wanted to discuss. Okay. Uh, yeah, everyone clear up until this point? I can repeat if you want me to.
Sir, once repeat, sir.
Okay, so I told you this sequence currents based adaptive protection scheme requires positive sequence current component and negative sequence current component, right? And the primary operating time is calculated. I use pointer. This primary operating time is calculated using a plug setting multiplier, which requires positive sequence current component, right? And the operating time for the backup relay is provided using negative sequence current component. So the plug setting multiplier to calculate the operating time for the backup relay uses negative sequence current component. So this negative sequence current component will only be present if there is an unbalanced fault or an unbalanced if there is an unbalanced fault in the system. If there is a balanced fault like a three phase to ground fault, so do you know how many kinds of faults are there? So I'm taking some things as assumed. So you can let me know if you don't know. You don't, right?
No, yes, sir. We know types of fault.
Yes. So, for a three phase to ground fault, which is generally balanced in nature, it is a balanced fault. There won't be any negative sequence current component present. So, the whole idea of getting this operating time for backup relay will be futile because there can't be a negative sequence current component. So, I just wanted to tell you that this scheme is applicable only to unbalanced faults, not to balanced faults, right? So using these two operating times, we can now perfectly calculate. Let's say that our microgrid changes operation from islanding mode to from grid connected mode to islanding mode, or islanding mode to grid connected mode. We will be able to calculate the kind of time multiplier setting that is required. So what does the time multiplier setting do? It adjusts the speed to trip the fault. So now we were able to find two things. One, we were able to find the perfect plug setting multiplier quantity using sequence currents. And then two, we were able to find time multiplier setting using this equation. But third thing remains, that is to calculate the direction of the fault. So the relay must be able to sense the direction the fault is happening. So for that, how do we do fault direction estimation using this? So they proposed, the researchers at IIT Roorkee proposed that we can use superimposed current. So let's say that this is a microgrid. This is a simple, uh, let's say three bus microgrid. So what they are doing is they are trying to calculate uh, they are trying to show how to calculate or how to estimate uh, fall direction using these superimposed current components. So I know this course right now in the present stage with protection schemes and all is a bit heavy, right? But bear with me. It's like 2 more weeks. You have to just bear with me. If you want extra information, you can extract. You can ask me. I don't know how much you know. I don't know how much of information you have. So if I don't tell you something, don't assume that I also don't know. Maybe I won't know, but at least ask so that we are both on the same page, right? So let's continue. Let's say there is a relay at G, right? And we have been connected. This microgrid can be connected to this grid, and it is connected to a DER. So what we want to do, how will this relay at G be able to sense if a fault happens at F1 place or an F2 place? So there are two kinds of fault happening. One is forward to it and one is reverse to it. So how will it be able to sense it? So what they did was they proposed that if we were able to calculate sequence components of the currents, we would be able to generate a methodology for this relay to be able to calculate the direction of the fault. How did they do that? They drew the So they started with drawing the positive sequence diagram, electric network diagram. Right. So what is a how do they do it? So we have this grid connected to bus number E. Let's call it the voltage at which it is operating, VE. And then there will be some what you say internal impedance of this voltage of this grid. Then this E bus is connected to this relay G, which is at G bus. This will also in turn have some positive sequence uh, impedance. We'll add that. Then there are unbalanced loads connected to it. So we can denote the load by this, which is also a positive sequence load. Okay, yeah. And then we have the G bus is connected to the H bus, and the H bus is connected to a DER, which will have once again its internal impedance and a voltage source representation. So we can draw a positive sequence electric network diagram using this information, right? Let's assume there are two currents flowing in these two loops. One is I0, one is IH0, right? And let's say we are trying to calculate how the G will react to some fault happening in front of it, either in front of it or backwards to it, right? So the pre-fault conditions before the fault took place, let's call the current flowing between G to H. Let's call it I pre. That is the current that is flowing. So it will also be positive sequence, right? We are drawing a positive sequence network diagram. Let's call it I1 pre. So this is the pre-fault current component flowing between G to H. And so how will this I1 pre be? So there is a current coming from VE. Let's call it IE. Ignore IE0 right now. This is to draw Kirchhoff's voltage law. I'll just remove this so that it's not. And there will be one more current flowing from this DR IH, right? Since the direction of the current we have taken to be in the opposite side, I1 pre, this would be subtracted from IE. So the free fault current will be something like this: current component from the grid and the subtracted from the current component from the DER, right? And if you do Kirchhoff's voltage law using by using these two loop currents, I won't do it. It will take time. So you will be able to come up with this expression. Uh, check. So this expression is Z1L by Z1E minus Z1P plus Z1L by QVH, which is equal to IH0, because this I1P is in the same direction of IH0, right? So Z1PQ is nothing but, I will just make things simpler. So first, let me tell you what Z1P is. It's Z1E plus Z1EG, and Z1PQ is Z1P plus Z1L multiplied by Z1Q plus Z1L minus Z1L square, and Z1Q is Z1H plus Z1HG. So you will be able to derive this formula using Kirchhoff's voltage law. I won't go into that. So yeah, so this is how you can now calculate what I1P will look like using this what you say formula, and you know that what the pre-fault contribution of both the systems would be. So you know IE, you will be able to calculate IH, right? So this is how you calculate it using uh, the pre-fault conditions. Now let's say a fault has occurred. So if a fault occurred, let's say fault at F1 took place. So if a fault at F1 took place, let's draw the diagram again. I would again request you to please bear with me. It's like it's a hefty topic, I know, but yeah, sorry, this is F1, this one is G, and G, then Z1L, then this is ZF1. There is some current going I1 F1, and then you have Z1GH, Z1H, right? So using this, if you again calculate by drawing this Kirchhoff's voltage law, you will be able to come up with this two things. The fault current will be something like this, right? And so this fault current will look something like this. So you now know pre-fault current, and you can now calculate the post-fault current, which is I1 F1. Similarly, for I1 F2, it would be something like this: I1 F2, I1 E F2 minus I1 H F2. Okay, so now you have three things. You have pre-fault current, you have post-fault currents for both the F1 and F2 faults. Now, what do we do? So even if we have it, what is the thing that we can derive from it, right? So now we want to be able to calculate how will the direction will look like. So if I say a fault happened at F1, the flow of current will be towards F1, right? So if the pre-fault current which is flowing from G to H, how will it look like? It will look like in the reverse direction. So what you can do is you can calculate the difference of these two fault currents. So I1 delta I1 F1 will be something like this, and delta I1 F2 will be something like this. So these are called superimposed currents because these will tell you if a quantity is negative. So if a quantity is negative, what will happen? You will be able to tell if the flow was upstream or downstream, right? So you got this. Great. Now, So you are calculating it. You will be able to do it, but how about calculating the phasors for it? Because at the end of the day, you require phasors, right? So what you do, you calculate phasors using this quantity, phi f1 and phi f2. Once you do that, the direction or the what you say, the direction of this phi f1 will tell you if the fault has happened reverse to it or ahead of it. So let's see. This is for downstream condition, and this is for upstream condition, I guess. Yes, right. So let's take a look at this. So we had. Let me take a screenshot of this. Yeah, is everyone following? I mean, I don't know if you're following. You can just let me know if you're not following. Okay, now we have uh, this three bus system. So let's say fault fault happened at F2 and the power is flowing downstream, right? Downstream means from grid to DR. Okay, if that's the case, can you tell me how would delta IF to look? Would it be positive or will it be negative? Will it be leading or will it be lagging? I just told you how superimposed thing works, right? Just a second. Hello?
No, sir. Your voice is not coming.
Hello? Now are you guys able to hear me? Yes. Okay. I don't know what happens with this laptop. This frustrates me. Okay, so what were we discussing? So we were discussing about let's say if a fault occurs downstream again. Uh, just bear with me. If a So I told you how superimposed currents work, right? How we will be able to sense direction using this and this. So if a fault occurs downstream, the flow of direction would be the G will sense current. Okay. Um, Let me try this again. So originally the current was flowing like this. All right. So now what happened was this the fault at F2 happened. So this happened. So the current will now stay the same. It will flow from towards from G to H only, and it will go down here to the fault. So the current direction is not changing, but there will be a delta, sorry, but there will be a delta IF2 component, right? And if there is a delta IF2 component, how will phi F2 be? Will it lead or will it lag? It will lag, right? It's it's in the same direction. It's how this polarizing quantity is again the pre-fault current. It's in the same direction. The fault current, this delta F2 is lagging by phi F2 degrees, and this will show that the direction would be forward, because since the phi F2, which is the angle, is coming out to be lagging, which is positive. Let's say the fault opens through F1, right? If this happens, the current will now force direction from in front of G to backwards of G. If that happens, this delta IF2, this phi F1 will now lead, because IF delta IF1 will be more than the pre-fault current angle. So this is how this fault current would be, and the direction would come out, sorry, and the direction would come out to be reverse since this is negative. So I would request you to go through the lecture if you haven't. So she has explained everything. I have also tried explaining, and I would request you to go through this again. If you find any trouble, write down in the comment section. I'm open to doubts as well right now, but you have to just tell me if you have doubts, if you didn't understand something. No one? Okay, so I will now assume that you guys understand it, and if you have trouble, please let me know in the comment section, or you can also ask doubts in the class as as it's happening. So this was one thing. Now the researchers, they felt that they are still not able to distinguish the type of DR connected to the system. So this was for a single DR, right? But as we know, the type of DR also affects the quantity of the fault current. So a synchronous based DR can supply 5 times of rated current as fault current, while an inverter-based DR, due to power electronics equipment clamping the rate of current, it could only swell twice the rated current, right? So if this is the case, what happens is, how do we adapt the technique to be able to sense the the kind of DR which is supplying the power, that is the amount of current that is coming through it. So what they do is they come up with a with an index. They come up with an index that since the fault current is less in inverter based DRs, they say that you add both the fault current, the difference of the superimposed component of the fault current with the pre-fault current, and the index would be given by this. For SBDRs, because the current component, the fault component is huge, it's 5 times the rated current, you subtract it so that both the indexes are on the same level. And if these are on the same level, what would happen? The relay doesn't have to focus on the kind of current inrush coming towards it. It would only focus on the index that it's given, right? So now you have to do one thing. It's that for inverter-based DRs, for synchronous-based DRs, you have to come up with this index, which is how the delta IF will be computed for a certain relay. And after it has been done, you can also calculate the fault current using this uh, expression, which is the addition of the positive sequence fault current with the negative sequence fault current multiplied by delta IF. And using the same IDMT characteristics which we discussed previously, you will be able to sense the same things. Now it's just that you need to calculate both for the the negative sequence current component. Before we were doing it for the positive sequence current component. Now they are saying do it for the negative sequence current component. If you do it, you will find the same phasor diagrams, and based on these phasor diagrams, how the quantities are leading or lagging the polarized quantity, which is the pre-fault current. The pre-fault current in this case would be negative sequence pre-fault current is our polarizing quantity. So polarizing quantity is that quantity based on which we tell what the direction of the current would be, the fault would be. So you come up with the same thing just for the negative sequence current component instead of the positive sequence current component. And again, this technique is only applicable to unbalanced faults because negative sequence current component won't be there for balanced faults. Right. And the instructor has shown a beautiful case study based on RTDS, a real-time digital simulator. And she has also attached the paper in which they have published their results. You are requested to please go through them so that you are able to be on the same page. So if you have doubts, let me know. Otherwise, I'm going to switch to the next topic. So what is happening right now, this protection, this relaying and the protective relaying, this is a very huge topic. But since we have to deal it within this smart grid course, we are trying to tell you only the important information, how adaptive protection is needed, how adaptive protection is inculcated in a relay, and how this whole thing is working. But yeah, if you feel overwhelmed with the kind of information that you are receiving, then I just have to tell you that it's just for a week or two, right? Yeah. So if there are no questions, we'll move on to the next topic, which is storage, and then we'll discuss operation of DC microgrid and operation of AC microgrid and finish it off with question and answer. So we discussed in week 2 and week 3 about, no, week 1 and week 2 about the importance of storage, how many different kinds of storage there are. This is just a refresher. So NP Padhy sir gave a brief refresher on it. So we started with importance of storage, and so a storage is very important from the point of view of how the grids are going to function. So renewable energy this renewable energy. So let's say the power produced by photovoltaic, like 6 to 12 only, 6 a.m. Let's say 3 p.m. So we can't predict the amount of power a solar or a PV panel will give us, right? Because it's dependent on A, weather, B, how the forecast needs the weather forecast to be perfectly accurate, right? But still, there are certain disturbances happening in real time. We won't be able to perfectly forecast the output from a PV output, this PV panel. So what happens in real time? This whole graph, which was assumed to be something like this, would be like this, or it can also be like this, right? So there are three things happening. There are two things happening. One is intermittency. We don't know if they are going to be available or not. Second is variability. They are varying in nature. We won't be able to match. So this varying thing is very important for us because it is feeding power directly to the grid. If it's varying so rapidly, there will be fluctuations in the power grid as well. There will be inculcation of harmonics in the system. So storage, what it can do is it can sense this intermittency and variability, and it can form the storage. So what we want is a perfectly normal output from this. And how will we be able to achieve that? What we'll do is we'll supply power during this phase through the storage. We'll store power during this phase, and then we'll again supply power during this phase. So what we'll do? So trying to we are trying to achieve a normal supply of power. This is I'm just showing for a flat profile. The power doesn't have to be flat from a power. I'm just showing this as an example. So a storage forms the battery, the PV by this renewables by supplying power when it's unavailable or varying rapidly in nature. Second is we can flatten the load curve. What do we mean by flattening the load curve? Let's say we have this load curve. So we have a diurnal load curve with something like this. We experience two peaks, one early morning and one late evening. So this is a very so what we have is we have rapid rampings. So we ramp down very fast and we ramp up very fast. So the thermal storage is the thermal plants that we have right now, coal based, their ramping is very limited, 3% to 5%, I guess, in 6 hours, I guess. I don't have the correct figure, just check. So it's just an rough idea that they have very slow ramping. And to be able to match these rampings, what we need to do is we need to flatten this curve. We want to flatten it. How will we do that? Let's say that we have let's say we want a load curve to be perfectly flattened. That is a flat profile, right? So what we do is we'll call on a storage. So the load is less than what we want it to be. So what will it do? It will store power. It will act as a positive load on the system, and here it will deliver power, so that the load profile is. So what we are trying to do is trying to flatten the load profile. Similarly, here also it will act as a load, supply power, and then load. So effectively, we are able to achieve a flat load curve. And a flat load curve is very easy to give power to using just thermal-based coal power plants. But we don't want to do that. We want we want to reduce the reliance on fossil fuels, and that is what it is doing eventually, right? So if we are able to form them in such a way that we are able to decrease the intermittency, we are able to decrease the variability and intermittency, we will be able to uh, integrate more number of DRs into the system, right? So we can, in a way, reduce reliance on fossil fuels, right? And and what happens is usually we also want to provide stability to the grid. How will we do that? So a grid requires two things to function normally. One, the voltage should be between um, uh, normal range, let's say zero point 0.9 pu to point zero point 0.9 pu to 1.1 pu, and frequency to be within 50 point, sorry, 49.9 to 50.05, right? And for this, what we do is we require PQ control. So to improve grid stability and to be, if we are able to modulate power from the storage devices, we can modulate P, as well as using converters we can modulate Q as well, and we can provide voltage as well as frequency support to the grid. Black start, it's like it doesn't require any time to start up or shut down. So for a coal based power plants, there is a minimum amount of time is required before it comes up to its rated power. But for storage, we don't require any such. We just click on a switch, we just start delivering power right away, right? So this is the importance of storage for a present day smart grid. Right? And there are three kinds of storage: non-electric storage. One is mechanical. These usually include flywheels or pumped hydro storage. We then have electrochemical, which is generally our what are I don't remember you. Sorry, uh, electrochemical. Yeah, I don't remember, but there may be some. So for thermal, we have hot steam based, right? So we can store, we can try and uh, increase the temperature of water to a particular level, so that we require less amount of uh, yeah, फिर आवाज गई क्या नहीं yeah we require सब कॉल कर रहे हैं Okay, so yeah, where was I? So we can store this energy in the increased temperature of water or steam, right? And use it for later purposes. So key features is what we want in our battery storages. It should match with the properties of the power system. That is, it should be able to perfectly manipulate voltage and frequency in such a way that it stays within perfect limits. Second, there is a requirement for storage capacity because of uh, because it's relevant to the power systems. Then we have a minimum storage period. So in order to be able to supply power, we need a minimum amount of before supplying it to the grid, we need some part of it to be stored in the battery, right? Before it is able to start providing power to the grid. Third, it has some charging and discharging time. It can't just start providing, it can do it quickly, but it has some amount of time to charge and discharge. Like your phone, it takes roughly around half an hour to 1 hour to charge perfectly to 100%, right? That's what it's telling about. Then there is a required energy density and lifetime. So each storage has a lifetime, like your phone's battery. Your battery also decays with time. It is not able to store the amount of charge it was at a particular once it was when it was new. Then you need perfect locations and environmental factors. And third, there are a minimum number of storage cycles before you can start delivering power to the grid. So there are some key battery terminologies. So these are generally battery duty cycle. So this is the sequence of loads to supply. Then you have cell size. So this is how the individual capacity or the rated capacity of a cell is. A battery is a cumulative of multiple cells. So it's the cell size tells us what is the rated capacity of a particular cell. Then you have equalizing charge. So what happens is not all the let's say your battery, it's not sometimes able to correctly predict the SOC of a correctly predict the SOC, right? Let's say it has 90%, but it shows only 80%. So what we do is we give a particular amount of equalizing charge which has a great voltage greater than the normal voltage of operation, rated voltage, so that the SOC could be, the inequalities of the SOC could be corrected. Fourth is a period. A period is the interval of time during which the battery supplies load. Then we have a rated capacity. So it's the total amp hour capacity of a battery. And then the state of charge, it's the amount of charge that a battery has at a particular amount of time. So these are some basic terminologies which we discussed in week 1, week 2 only. Battery modeling also we discussed in week 2. You can refer the YouTube lectures for week 2. And it's just that the battery is modeled using a RC circuit. It is a first order circuit. Then if you increase the number of RCs, the better uh, you are better able to predict the sorry, you're better able to predict the quality, or your quality of model increases with the number of RC models you have. And the SOC is usually modeled using this. It tells you the using the battery capacity how much the SOC would be at a particular amount of time. This all we discussed in week 2. I'm just giving you a brief recap. So, but there are some factors that affect the battery's performance. These generally include the voltage that you give to a battery. You can't exceed a particular amount of voltage, and you can't decrease the voltage level when you are discharging from the theoretical value. It will decrease the life cycle of your battery. Second is the state of charge. So state of charge, if you have, let's say, if you drain the battery quickly, the SOC will fall faster. And if the SOC falls faster, the amount of performance you want from the battery won't be optimum. Then you have mode of discharge. So there are certain ways in which you discharge its constant current, constant power, and using this you discharge your battery. Dependent on the mode of discharge, your battery performance could be affected. So for this, I would like you to refer to IEEE standard for battery in EVs. They have this curves which tell us at what point the battery charges using constant current and at after what time the battery charges using constant voltage. You will be able to better appreciate how the mode of discharge affects the battery's performance. And then temperature of battery. So you must have seen batteries catching fire in India. It's because of the tropical weather. So if the temperature of battery exceeds the threshold optimum value, your battery will catch fire and its performance, if it's catching fire, its performance obviously will lower, right? Then service life. So there is some life to your components. I mean, your battery would start, your performance would start degrading once your battery's service life decreases. Then you have charging voltage. If you charge it greater than some volt threshold voltage, your battery's performance won't be great. Battery age, older batteries perform poorer. So there are some factors that I discussed which affect the performance of your battery. And all of these batteries supply power in what? They don't supply AC, right? What they supply is DC. So these batteries, when inculcated in the DC, and since these are DC, they're the microgrid that they refer to are called as DC microgrids. So let's discuss the importance of DC. So if we use DC transmission, like we have HVDC right now, high voltage DC, it's between northeast to Agra, I guess, somewhere there is a very big HVDC line. So if so what we do is when we use batteries to supply power to an AC grid, we have to convert the power to using some inverters or AC-DC converters. So what we are doing is we are using converters which are expensive and their maintenance is also expensive, right? If we use DC, if we implement DC all over the world, the transmission will also be DC. The impact, this conversion stage could be uh, neglected, and the overall system efficiency can be improved. Second, we won't have problem of harmonics or reactive power because these are the things which are present in AC because of fluctuating voltage, fluctuating this power voltages. In third, we don't require synchronization. So you know that when we try and integrate a synchronous based generator to, so you must have seen that if you want to integrate multiple synchronous generators into a system, there is this thing called parallel operation where you first synchronize one and then you connect it to the grid. So the synchronization issue is not needed because the batteries can just be connected to this DC bus and can start delivering power instantaneously. So eddy current, hysteresis losses, and skin effect, which are major problems in AC, are usually neglected in DC. Third, so due to better management, so you have the congestion of transmission line could be reduced and your conventional grid could be alleviated from a certain amount of stress, right? So these are some importance of uh, DC. And this is indeed true, right? Now you're using EVs. EVs are what? These are batteries, mobile batteries, which are DC in nature. And then you have batteries that are DC, your computer, your laptop, your phone, everything surrounding you made of batteries or battery-like components. These are DCs. Even PV, your photovoltaic PV plant supplies power in DC, which you convert using an inverter, right? So since all of this is DC, why not have DC microgrids instead of converting them using conversion converters? So like you see in this diagram, first diagram, uh, you'll see that supercapacitor, battery, wind, fuel cell, photovoltaic, all of them can be converted using converters. So so this supercapacitor will require only a DC to DC converter because it supplies power in DC. Then battery is also DC. AC wind generally has turbine which is connected to synchronous alternators. There you need to convert it to DC first. Fuel cell supplies power in DC and photovoltaic supplies power in DC. And your data centers are all DC in nature. Your communication towers are DC in nature. Heating equipment and lighting loads all are DC. So if you integrate using one bus, you can have, which is called a DC bus, you can have DC microgrid enabled. So this topology is generally called single bus topology. because there is only one DC bus. So uh, you can have flexible control using these multiple DC-DC and AC-DC converters, right? Then there is one topology called multi-bus topology where you have you increase the number of buses and then you have a reconfigurable DC ring. This is called DC ring topology, where you have a ring-like structure and you connect your equipment using uh, converters or DC into a DC bus. So this increases reliability since this topology is highly reliable in nature, right? Okay, so yeah, so this PV curve, how did this come into picture? I already discussed at length in week two. You are more than welcome to go through the week two slides or YouTube lecture. Okay, now I told you about the importance, I told you about the advantages of DC, but there are some impracticalities or some challenges faced by DC microgrids as well. First of all, IEEE or other IEC institutions don't have many standards for DC microgrids because we still have we are more majorly dependent on AC based resources. Third, we don't have we have protection issues because we don't have DC kind of circuit breakers. There is a lack of DC infrastructure because all of our infrastructure is based on AC transmission. Circulating currents in parallel operation and grounding issues are some things that are present in DCs. Circulating currents are generally those currents which revolve back and forth. And yeah, so all the industrial loads, 90% of industrial loads are still AC. These are inductive loads. So inductive loads are generally AC in nature. And DC won't be able to feed these AC loads until unless there is a converter in place. Last, there is a high power loss in low voltage DC distribution networks. So, since this is the case, how will we? So, these are some things which hamper the growth of DC right now, but we still have AC based microgrids. So, which we were discussing up until now. So it's nothing. So we can have microgrids of anything, DC microgrids. It's just that the microgrid. What is a microgrid? It is an electrical uh, system which has multiple generations and multiple loads, right? It can supply generation, it can supply loads as well, and it can be connected to grids as well. So if it is whole DC, it's called DC microgrid. If it is having AC components to it, it's called AC microgrid. Right. So this is how a structure of a typical AC microgrid look like. We have already dealt with in our week four lecture when we were discussing the islanded and grid connected mode of operation. So, so there are two kinds of operation. Again, I will write. One is grid connected mode. Oh, sorry. And the other is islanded. In grid connected, you are connected to grid. Islanded, you are disconnected from the grid. But islanding has certain issues, like we've already discussed. These have, if they are not detected properly, they can cause voltage to fall. There is a lack of protection. We can face, it can be detrimental for our crew workers or workers working on certain lines. But still, islanded mode of operation is required sometimes. Let's say you're experiencing disconnection from the grids due to some fault or some disturbance. You still would want your hospitals, your critical loads to be able to supply it, right? So these critical loads can be supplied when the microgrid works in an islanded mode of operation. But for that, you require control over your distributed generations. For both of these grid connected control or islanding mode, your DGs need to be controlled and they need to be controlled so that the grid reliability is maintained at all times. Right. So there are two kinds of uh, DGs, synchronous based DEGs, and then you have inverter based DEGs. Control of synchronous based DGs are very simple. What you do is you control how the um, the how the prime mover, how the energy that is being admitted into the prime mover is uh, is regulated, right? So what happens is, let's say you experience change in load, so you would want to change the speed of your generator to be able to match the load, right? So that is how you control it. There is one thing called AGC, which is automatic generation control. This automatically controls the speed of the DER, synchronous based DERs, to match the load at all time, and implements droop control as well. So what happens in droop control is your power versus frequency curve is something like this, right? Let's say this is your perfect frequency at which, let's say it's 50 hertz, right? By some mistake, you experience that your frequency has fallen to this place. If that's the case, what happens is your if it falls, that means this your power being supplied by the generation has increased. So if that's the case, what would happen is, what did I just say? Okay. Oh, no, 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 sorry. If a frequency falls, let's say the new mode of operation comes up with this P dash uh, frequency, right? So what you have is, if P generation is less than P load, your frequency falls. If P gen is greater than P load, your frequency increases. Let's say your new frequency is F dash and it requires P dash amount of power. What you do is you increase the power being supplied from your generator. So you increase it like this. You upscale the graph a bit. If you do it, sorry, so this would be your P dash that is required, and this would coincide with your F naught frequency. So once you upscale it, what happens is your frequency goes from here to here, and then it goes from here after you upscale it, so that the frequency comes back to its nominal point. So this is the droop control in which your synchronous generators are controlled. But your inverter based DGs are controlled using the inverters that are connected to the DGs. So these inverters are of different types. For grid connected mode, there are two kinds of strategies. One is grid feeding strategy, which has grid feeding converters and grid supporting converters. And in islanding mode, you have grid forming, grid feeding, and grid support converters as well. So, yeah, where was I? So what you do is, So, um, so this is how you control your inverter-based DGs. So I would request you to please go through this week's fifth lecture to learn more about these strategies. I have, due to paucity of time, I have to increase the increase the speed of this lecture. Okay, uh, right. So now I told you about how we control these DGs, right? Synchronous generators, you control it using loop control, and which is generally an AGC as well. And you have inverter-based DGs, which have converters, power converters, and each grid connected mode and islanding mode have different strategies, right? So all in all, the operation of microgrid is to provide support services to the system. So what they do is they provide support to the overall grid. So ancillary means support. So microgrid provides support services to the grid. Now there are different kinds of support services it provides. Under grid connected mode, it provides frequency and voltage support, and in and also it provides reduction in grid losses. Let's say earlier the amount of power coming from a far off place, you had a higher number of I square R losses, right? So what you did, you installed an microgrid at the remote place. When the microgrid was connected, you don't have to supply power from that far off place, right? So that I square R losses could be reduced. Then it can be used for congestion management. Let's say there is a line. Okay, there is a load. This is a generator. It can, let's say, supply 250 megawatt, and this is a 100 megawatt line. So up until 100 megawatt, it was fine. This generator was able to supply it because the thermal limit of line was 100 megawatt only. But as it increases 120 megawatt, since the line will now be congested because its thermal limit is 100 megawatt, this generator won't be able to supply power to this load. So what you can do is you can connect a DER, you can make this a microgrid, and this DER can supply power to this grid. So it can supply the remaining 200 megawatt. Sorry, 20 megawatt. So it can be used for congestion management as well. Third, since you are providing frequency and voltage support, you are also improving harmonics, power quality, let's say. Right? So your overall power quality of the power will also increase. For isolated mode, you can do two things. Either the whole grid becomes grid forming, that is, it decides the voltage and frequency of the whole operation. And third, it can also provide black start opportunity. That is, let's say there is a complete shutdown. That's what happened in 2012 June, right, in India when the whole northern grid failed. So, in order to black start, what you can do is you can empower localized grids, microgrids, and then these microgrids can be used to support the main grid. So, these are some ancillary services that can be provided from the microgrids as well. So, this is all. If you want me to discuss about these strategies, let me know. I still have some time. So, were you able to follow today? I mean, there's only one person. Dharmender ji, were you able to follow? If not, be frank with me. I mean, I want honest feedback. There's only one student. I guess people didn't know about this class or something like that. I announced. I don't know why people didn't join. Yeah, maybe they had other issues. Okay, so no feedback, no questions, no doubts. Am I audible, right? I'm audible. I think it's blinking.
Yes, sir. Audible, sir.
Uh-huh. Any doubts? Any feedback? Do I go fast?
Yeah, actually, I have studied a few lectures of this week.
Oh, okay. I mean, these are supplement to it. I mean, see, you have to go through all of these lectures to be able to understand what I'm going to teach because I just teach a
Yes,
gist
sir.
of it.
Yes, sir.
Rest everything is covered by the instructor. I can't go through everything in 2 hours. It's it's it's
Yes, sir.
uh,
Yes, sir.
it's difficult for me as well, and I had to rush this whole thing because I have to leave tomorrow and I have lot of work this week. So had I had very less time to prepare for this class as well. I take some time to prepare so that I'm able to deliver the lecture appropriately. I mean, I'm still learning to deliver lecture. So if there are feedbacks, so do I go fast? I don't know. People think I go fast.
No, sir. It was good, sir.
Okay. Okay, let's do question and answers. Let's see how much you could gauge. So, first question, if the fault current seen by the relay is due to the contribution of only IBDRs, then delta IF is expressed at. Eh, remember, I discussed in the second method this thing, how the index would change because the inverter based DRs experience less amount of uh, this, fault current, which is twice the rated fault current. So, what do you think would be the index? I just discussed today. So, let's give you a brief recap. This. So because the amount of current being seen by the inverter based DR is less, the index that we use is this, where we add the pre-fault current to the fault current, to the superimposed fault current. For SBDR, where the this current is 5 times the rated current, what we do is we decrease the delta IF by subtracting the pre-fault current from the superimposed current. So the answer is C, right? Okay. The lower and upper limits for the TDS are set to. Can anyone? This TDS is nothing but time dial setting, which I referred as time multiplier setting. Both are same. Hmm. So what do you think the answer would be? So always remember this TDS, if it's close to 1, and TDS if it's far from 1. So TDS is the same thing. It's a time multiplier setting. I mean, there is no difference. It's just that it's a different terminology used. So if it's close to 1, what happens is you increase the operating time of the relay, and if it's far from 1, you decrease the operating time. So since the threshold is 1, your answer would be the first one. So the lower and upper limits are nothing but 0.05 and 1. Third, the polarizing quantity in superimposed positive sequence method of all direction detection is, I just discussed.
Sir, pre-fault current.
Yes, it's the pre-fault current. You use it to be able to tell what is the direction of the, yeah. Second, fourth question. So in our fourth week, when we were discussing about relays, I told you these relays are connected to CT, which is a current transformer. So, uh, so now tell me, if it's connected to a current transformer, how can we change its plug setting? It's through number of ampere turns. The number of turns around the CT coil is what can be used to change the plug setting of the relay. Always remember, because it's connected to a CT, which is a current transformer. Yeah, in a static overcurrent relay, inverse time characteristics are obtained by, I don't think you know this answer, but the answer would be an integrating switch circuit. I don't know why it's there and why they asked. Okay, next question. In which mode of operation the fault current in the microgrid is high? Who can tell me? Think about it. How the fault current would be, the contribution of the fault current in grid connected mode and in islanding mode. The contribution of fault current from the grid side and the DR side in both the grid connected and islanding mode. What do you think? In which will it be high?
I think, sir, islanding mode.
No, it would be grid connected mode. So let's say you
Okay.
have a grid and you have a relay, and there is this DR and a fault occurs. So the fault will come, current will come from the grid side plus the DER side if it's connected to the grid. Let's say the switch is opened. If it is opened, this current would be 0, and the only current will come from the DER side. So the contribution of the current would be higher in grid connected mode, not in islanding mode. Is this clear, or do you have questions? Clear, right? Okay. I'll assume it's clear because the contribution would come from two things in grid connected mode and only from the DR side in islanding mode. Next question. Due to the bidirectional fault, which types of traditional relays are unable to provide safety operation? Tell me.
I think so, all of the above.
Yes, it's all of the above. Both distance relay can't sense the direction, unidirection, its name suggests it's unidirection, and instant overcurrent relay can't sense the direction of it. Next question. While estimating the fault direction using the superimposed current, the sign of delta phi during the reverse fault when the power flowing in the upstream direction is. So again, if the power is okay, reverse fault, this is G. Always draw a diagram so that you are able to understand. This is grid. This is where the relay is connected, and this is your DR, and the power is flowing upstream, and the fault occurs behind. That means here, fault. Now tell me, if this is the case, what would be the direction of phi? Hmm. Now tell me. So it's saying upstream, reverse. So the direction is positive. How? What's happening is your current is flowing in the same direction. But the relay, which is sensing the current will come from, sorry, the current it sense will be like this. Even though it says upstream, the flow is upstream, but the current is sensing, the relay is sensing that the something has happened behind to it or behind the original flow of power. So if that's the case, this delta IF, which is nothing but IF minus I pre, this thing would be positive, and if it's positive, the whole angle would come out to be positive. Second, third, whatever this is. In the two bus system, the load is drawing 200 ampere current from bus 1 to bus 2. After fault, the current at bus 1 is increased to 1500 ampere. Then find the superimposed current at bus 1. So I just told you, superimposed current is given by this, which is IF minus I pre. So previously it was 200, after fault it was 1500, the answer comes out to be 1300, right? I don't know why I'm getting this feeling you are not understanding. Okay, no worries. Third question. The converters used for battery, PV, ultracapacitor, and PMSG wind system in a DC microgrid respectively are. Okay, answer me this. So a battery can charge and discharge, right? It can charge as well as discharge. So it can act as both ways. It can supply as well as it can act as load. So it will require a bidirectional uh, converter, right? A PV, will it require a bidirectional converter? Can it act as a load? Will it take power? It won't, right? It supplies power only. So what it requires is a unidirectional converter. An ultra capacitor. So let's say a capacitor is connected to certain load, and there is some as well, this switch is happening. So what it does is it maintains a particular voltage, right? So when the switch is removed, it can supply power, and when the switch is added, this load can this generator can supply power to the load as well as to the ultra capacitor. So it would require what? A bidirectional converter as well. What about PMSG? Does it require bidirectional converter or a unidirectional converter? So it is a unidirectional converter, right? So the converters used will be bidirectional, unidirectional, bidirectional, and unidirectional. So the correct answer is A. Okay. Last question. The following type of inverters may not be suitable for the grid connected mode. Can you tell me which one? Okay, let me tell you. So the grid feeding converters, what they do is, okay, so they are used to affect changes in voltage and frequency by using PQ reference. So what they do is they use this reference, adjust PQ according to this reference, and affect change in the voltage and frequency of the overall system, microgrid, sorry, through which it is connected. So the grid feeding converters generally require this reference to be able to match or adjust the power and this real and reactive power. Due to the need of real and reactive power, these can only function in grid connected mode because they need this reference from grid. The grid forming converter, on the other hand, are the ones which come up with this voltage and frequency. These maintain this voltage and frequency by affecting changes in PQ only, but they don't require a reference because they set the voltage and frequency of the whole system. So if they, so these don't need to be connected to a grid connected mode. Grid supporting mode can be used with both uh, grid connected mode as well as this what you say uh, these can be
Islanding.
islanding mode. Yes. So if they are being used for both, what they do is they are supporting the grid in both the mode of operations. So they can be used in both grid connected as well as uh, islanding mode. So only the grid forming modes are not suitable for grid connected mode because they are the ones who tell what the voltage and frequency of the system will be. Next question. Grid feeding converters are connected to the grid in dash to inject power to an energized utility, right? They supply power. How? What are they connected to? They are connected in parallel with a high impedance. Why do they do it? Is because of the fact that they since what happens is they can change, they can affect power, inject power, and this injection of power must be limited because if a fault occurs, they will supply a very large amount of current to the inject a large amount of current into the system. To be able to dampen these currents, to be able to dampen these disturbances, we require a high impedance which limit this current. So the grid feeding converters are usually connected in parallel with high impedance. Second question, which of the following battery is suitable for laptops and EV applications?
I think, sir, lithium ion polymer.
N- No, it's just lithium ion. A polymer is it's a derivative which is used not for laptops and EVs, but for other purposes where the lithium ion, using lithium ion would be very expensive. But in your laptops, in your electric vehicle applications, you will have only your lithium ion batteries
What
because
is the
these
polymer? Polymer, lithium ion polymer.
so a polymer could be manganese or some other ion which is connected to the lithium ion to be able to uh, decrease the amount of lithium which is required to make a battery. So, sir has discussed this in his lecture. I don't have um, a perfect explanation of the polymer that is required. So, you may have to go through that lecture.
Okay, sir.
Second last question. Which of the following operating mode of voltage source converters is suitable during both islanding and grid connected scenarios? I just told you.
Grid supporting mode.
Yes. It's the grid supporting mode. They can be used to support the grid in case of emergencies by in both islanding and grid connected mode. Last, which of these is not the microgrid ancillary service during the grid connected mode? So, to be able to do frequency control, you need to be able to be connected to the grid so as to see what is the voltage and frequency of the grid to be able to support the grid. Congestion management only can be done once you are connected to the grid, because if a grid is unable to supply power to a certain place, the microgrid is able to provide that power, and it can't do until unless it knows that it is required to supply power to that point. Power quality can only be improved when it's connected to the grid. It's the black start, which is the ancillary service during which is not there when it is connected to the grid connected mode. That's what just I explained here. Okay, so this is what I had to discuss in this lecture. If there are questions, or if there are other questions that are not within the scope of this lecture, I'll be happy to answer.
Thank you, sir, for such
Uh,
nice
I don't
lecture.
know, you you don't answer all of my questions, but even if it's
No,
nice on.
actually, sir, I have not studied well all lectures. That's why
Hmm.
today I am unable to answer all the questions. Max.
Why what happened this time?
Actually, sir, already some classes are going on. Basically, I
Oh,
am teaching
oh,
uh,
you, where do you teach?
Galodia University, Greater Noida.
Oh, Belgotia University. Nice. So what subject? It's electrical only.
Yeah, actually, right now I am teaching electrical machine and basic electrical engineering.
Oh, nice, nice. I took classes for basic electrical machine last
Oh, great,
year.
sir.
Yeah.
Actually, sir, right now I am doing four courses on NPTEL.
4 courses. I how
Yes,
why?
and actually regarding some PhD work.
Oh, you're also doing you will be joining for PhD, I guess.
Yeah, yeah, from NIT Patna.
NIT Patna. But you are in you work in Gurgaon, right?
No, no, Greater Noida, UP, Noida.
Oh, it's Greater North. Still UP, right? It's UP and Bihar, opposite directions.
So actually, right now I'm working in Greater Noida
Mm-hmm.
and pursuing PhD from NIT Patna.
Oh, so you're
But
already there in NIT Patna. Under
yes,
under
sir. Yes.
which professor? What are you working on?
Actually, AGC, Automatic Generation Control,
Oh,
and my professor name is Dr. Ravi Shankar.
oh. So you should have told me now when I was explaining group control.
Yes, yes. Actually, I understand, sir. Yeah, like frequency and yeah, load changes.
So my work, I also work in power markets. So my power
Oh, great,
markets,
sir, great.
so in close proximity to power system operation. So it's all how NLDCs work. So the main focus of NLDC is how they inject, how they control the AGC. So POSOCO is our NLDC, right? So they supply the signals to AGCs of different generators connected to which are connected to this NLDC. So they are the ones who supply signals to this AGC. But I don't work in that area. I just see how power market operations could be used to benefit the power system operations as well. So, like if you need frequency support, let's say how the system operator could buy that frequency support from that market, and how markets could work in tandem with that system operation. So it's close proximity. I mean, it's not similar, but yeah, it's in same direction. Yeah, nice to hear someone working in the similar field. I only find people working in power electronics for some reason.
Yes, sir.
Yeah, so again, that's nice to hear that someone from industry or someone from academia is also in this course. That is wonderful to hear. Okay,
Sir,
so
already I have done this course, 8-week course by NP Padhy sir in 2018.
oh, you've already done it.
Basic, yeah, basic introduction to smart grid.
Oh, okay. Yeah, yeah, he
Yeah,
has one course which is very basic. Yes, yes, yes.
yes, in 2018.
So how is the level? Is this too advanced or close to it?
Uh, uh, yeah, something is advanced as compared
Some
to the basic course, right? About 60 to 70% are same
60 to
at now.
70. Oh, so what they are doing is they build on, so they, whatever the concepts they taught you in that basics course, they are just teaching three more
Yeah,
steps ahead
uh,
of that. Protection wasn't there, right? Protection wasn't
yeah,
included in that
protection was
course.
there, ice landing. Yeah,
Oh, but
I,
here this protection is a bit tricky part because people are not familiar with how relays work, how what are IDMT relays, these distance relays, modes relays. So if people don't
yes,
have idea about basic relays, I can't, I have to just teach them what happened during that week, right? I can't teach outside of the course because if I start doing that, I won't be able to complete my week six or the week lecture that I want to teach.
yes, sir. Already
Some
protection is a broad.
Yeah, but what I think is people don't understand that people come into this class thinking that they'll get everything what has been done in this week, which is impossible, and they stop they start losing interest. So once they start losing interest, there's no coming back, right? Right now, only one person is connected. I mean, one person. It's very bad. I don't feel good today.
No,
But
no, no,
anyways.
sir. Actually, because some person has work in evening, maybe some person see your YouTube lectures.
I don't know. I mean, I don't see any difference, but yeah, it sometimes becomes disheartening, right? You come prepared, you want to teach, and then it's just one person connected. I mean, anyways, this it was nice knowing that someone
If
is
there is
so
no
you.
interaction from student side, so I thought whether I am going in right way, other students are understanding not.
Okay, so you are also registering for exams then, right? So you will also give
Yeah,
exams
yeah,
or
yes. I have already registered for exam, 4 exams.
for what are the four courses have you taken?
Control engineering,
Okay.
and one is the smart grid, that, and
Hmm.
second one is the non-conventional energy resources, IIT Madras,
Okay.
and one course from IIT Kharagpur,
Power
distribution,
system.
I think, operation and distribution system analysis, I think, like
Oh,
that.
distribution system analysis. Oh, that's a
Yes,
wonderful
yes.
course. It teaches about how different kinds of feeders are there, how they're connected and stuff
Yeah,
like
yeah,
that.
types of feeder and percentage voltage drop and
Yeah, yeah,
load factors like that.
yeah. I was
Yeah, yeah.
interested in teaching that subject, but I got this subject. Anyways,
Okay.
it's good. Good to hear.
Sir, I have visited NP Padhi sir lab and
Oh,
in IT Roorkee in 2019.
oh. So you must have met his students as well, right?
Yeah. Student and also with NP Padhi sir because he came regularly in our college for FDP. Okay.
Oh. Hmm.
And yes, but right now sir is in MNIT Jaipur.
Jaipur, yeah, he's director. Yeah, so his student, so Guru Raj sir, he recently joined, not recently, he joined in 2021 as faculty
Yeah.
in IIT Kanpur only. So I
Yes, sir.
think you
Yes.
must have met him during that time. He was there only.
Yes, sir. Actually,
Hmm.
one conference in 2019, National Science Conference, I think, National System Conference, like
NPSC, National Power System Conference.
National System Conference. So
Hmm. Hmm.
I was one paper at that time.
Oh.
So I moved to the sir also, and already I have done the recently course of introduction to smart grid,
Hmm. Hmm. Hmm.
and one course already done by sorry, taught by I think Kumbhar sir in electric department.
Okay.
Ganesh Kumbhar, right, in IIT Roorkee itself.
Oh.
One more professor.
Hmm. So,
He started the electrical distribution system analysis.
Okay.
NPTEL.
Okay. So you met anyone from IIT Kanpur up until now?
Yeah,
I
yeah, Dr. Essen Singh, sir. Dr. Essen Singh.
Oh, he's my co-guide.
Oh, he's
He
also my co-guide.
Oh, he's also your co-guide.
Yes, yes. Right now he's in Triple IT in Gwalior.
Yeah, triple IT Mole. He's also my
Recently,
co-guide.
sir has visited my university as a chief guest IEEE conference.
Oh, yeah, I didn't
So
know.
I meet to sir. Yes, yes.
Oh, very nice. You're a fellow student. Yeah, right. We are under same supervisors. I didn't know.
No,
Okay.
no, sir is very quiet nature and very peaceful.
Yeah,
Uh,
he gives wonderful replies whenever asked. I mean,
yeah, yeah, definitely.
and he gives it very quickly.
Yes, yes, sir.
He's a very calm personality. He visits us regularly. I mean, there are many of his students working under him right now in IIT Kanpur only. He comes every
Yes,
3 to 4 months to meet all
yes,
of us and discuss what are some challenges that we are facing or anything that we wanted to discuss about research.
yes, yes, sir. This
That's
is
something
very
that I
active and energetic.
and yeah, very diligent with his duties. Yes.
Yes, sir. Yes.
Nice to hear that you're working under the same professor.
Really, I am very glad because you meet
Yeah,
such nice.
next time you meet, just tell him that you were in the same course that I was teaching. He would be very fascinated to know that.
Yes, yes, sure, sir.
Okay, nice talking to you, Dharmender ji.
Sir, you can you give you a mobile number in your WhatsApp chat because it's a
Uh,
chat
so
box.
just let me pause the recording. Yeah, so this is my number. You can just message me so that I can save your number as
Yes,
well.
sure, sure. Sure, sir.
Hmm. Okay, Dharmender ji, it was nice talking to you.
Same here, sir.
Let's meet next week as well, Saturday 6 to 8, regular classes. And yeah, so goodbye, good evening, good night.
Yeah, good evening, sir. Thank you.
No worries. Okay.